Was it? How's the training of the new person? When do you go to Virginia? May 6th. What day of the week is that?
Friday, the next Friday.
Okay, so you'll just miss Friday?
Yeah, and then
Okay.
Dead Day.
Yeah, Dead Day is dead. But you'll be back after Dead Day. Okay. All right.
A night. We leave like Friday morning at 6:15, and we get back Monday night.
When's your finals?
Not until like Thursday.
Oh, that's good.
Yeah. So the only one that's like technically on Tuesday is for applied stats, but it's a report.
Yeah.
It's a report, so you can do that anywhere.
Exactly.
Turn it in anytime.
Thursday before this one.
You wanted to change the date on that, right?
Probably
Yeah.
11.
Okay, that's fine. Just let me know when you have a decision. I'm flexible about that.
They're also right after.
Don't tell anyone.
I'm gonna do it like a Tuesday or Wednesday.
Don't tell anybody that I'm flexible.
Flexible with what?
So you can keep telling everyone that due dates are arbitrary.
Well, due dates are arbitrary, are they not? I mean,
For sure.
except that you don't want to put things off, because I find that when the student comes and asks for extra time on an exam, or extra time on an assignment or something like that, inevitably what that does is it pushes it off into something else that then they need extra time on that, and it just kind of all snowballs. So when I have a student who wants additional time on an assignment, I'm always interested in, okay, what is that additional time going to facilitate you doing? Like, how are you going to use that additional time? What's your plan for that? Because if you don't really have a plan for it, then me giving you extra time doesn't really gain you anything, because all it does is give you more time to procrastinate doing whatever it is that you're not doing right now. But I had a student last semester who came to me and had an accommodation that allowed for more time on assignments. And I'm like, okay, well, what are you going to do with that? Like, what is it that's causing you to not get the assignment done? And she's like, well, I really don't understand. It was a literature summary. She's like, I really don't understand the paper, and so I can't really see how I can write a summary about the paper if I don't understand the paper when I'm reading it. I'm like, oh, so what you need extra time for is to have you and me sit down, go through the paper, make sure that you understand the paper. And so we scheduled some times to just sit and talk about the paper to make sure that she understood the paper. And at that point, she felt much more confident about writing the paper. So for me, I don't like putting things off, because that then just tends to stack up on other things, and then it just makes your life more chaotic rather than less chaotic.
And it's a problem for tomorrow. Oh no.
Is that a problem for tomorrow?
No, it's gonna be a problem for tomorrow, so it feels better.
Oh, yeah.
I have that issue a lot.
That's ultimately not productive, though. That's
No,
ultimately self-destructive.
It is very.
Yeah.
It's a terrible mindset, but like honestly, it's
But sometimes it's like really useful for me because I am like constantly anxious about everything. So especially with things that it's like I can't do anything about that right now, it's helpful to be like, that's not a currently issue. You can worry about that later. That's tomorrow's problem, but not right now.
I've never heard it phrased like that, but that's interesting. I'll have to put that in my way of filtering things. So that, to me, that's what the beauty of a deadline, though, is, something that has a firm, hard deadline on it. You get that done
Yeah.
because there's a deadline.
yeah.
No,
Yeah.
I very much appreciate having deadlines because if I didn't, I would never do anything.
Yes.
Facts. I took an online class in high school, and I just had to turn everything in by the end of the semester.
Oh,
Literally did it like worst like last 2 weeks of my life was like sitting there doing it was a very like odd class. I had to do a bunch of interviews and I was like, oh my god, I have to interview 14 different people. Maybe not 14. I think it was like over 10. But I was like, oh my god.
well,
I really,
well, welcome to academia. Essentially, I get home in the evening and making dinner, and Elizabeth is like, not you, Elizabeth, my Elizabeth. Elizabeth.
You say that, it takes a second.
Elizabeth's like, so what do you need to do tonight? Like, everything and nothing.
I have 0 concept in time. So it's like either everything's due tomorrow when it's really not, or
Yeah,
everything is due in 3 weeks when it's due tomorrow. So
yeah.
it's like there's no difference. It's either getting done now when it doesn't need to be, or it's not getting done.
In theory, one of the things college should be teaching you is how to survive life. It's good to know that you guys are not learning those lessons. All right, let's talk about sex allocation instead of life. Although sex allocation is about life to a certain degree. Um, so we have class today. Then we don't have class on Wednesday. We will have lab on Thursday because I want to talk to you about the data that you guys generated and about what that lab report should look like. But probably won't take the whole time on Thursday. And then we'll have class on Friday, and then we'll have class on Monday, and we have discussion on Wednesday, and Emily is leading that discussion because you guys have already led discussions. Just so you know, have you guys started reading Kroll and Hodel yet?
No.
Okay, start reading that. It's actually about frog mating systems.
I tried to get a paper.
Did you?
I was like at it yesterday, and I was like, oh, I read a paper by then, and then I was like, oh, it's this one. I don't actually need to read it right now.
Okay. Yeah, so for me, it's a pretty easy read because it's about frog mating systems, which is something that I find fascinating. But I know that students have had difficulty grabbing hold of all of it in the past, so don't put off reading it until like a day or two before. You might want to give it a quick read earlier than that because it's a pretty complicated mating system. And there are lots of territories and things are going on differently in each male's territory depending on characteristics of the territory. So it is a it might seem straightforward when you first look at it, but it actually ends up being much more complicated than that in the end. So give yourself enough time to give that some good thought because it's more involved than you expect it to be, according to feedback from previous semesters of students who have read the paper. What was your thoughts on it when you read it for your literature review?
I don't know. I didn't think it was too bad, but I also didn't focus a lot on like the methods and results section because it wasn't when I was like
Okay.
putting into my
All right.
paper. So
Okay.
I need to go back and like read those sections more in depth.
Okay. All right. So so sex allocation. We've talked so far about sexual conflict, investment by males and females in reproduction as a whole, and how those investment decisions can lead to sexual conflict because one individual is investing more in reproduction than the other. We've talked about all of the factors that influence that and how that then affects things like parental care. Um, but we come to this section of the book where they talk about the fact that we normally think of sex ratios as relatively set because in human beings, the sex ratio is about 49% female and 51% male on average. We have what's known in the business as kind of an even sex ratio, 50-50 mix.
Before I forget,
Yeah,
when is the calculator live report due?
we haven't discussed that yet.
Okay, cool. Sorry, I was just looking at things I had on my to-do list and wanted to make sure I didn't miss
We had to put things off, so the due date for it isn't correct in the schedule. Be thinking about when you guys want to make that due.
Never.
Except for never. Never doesn't really work.
I also vote never. I assume Mason will probably vote
I think
never,
that's
so that's
majority.
3-1.
This is a point where democratic rule breaks down. Never is not on the ballot.
How about
Macron and Le
August?
Pen are on the ballot. Third option, not on the ballot.
Is August an option?
Um,
What if we just subs it for like final?
what?
As like just subs it for the final. No final.
Well, because I have to give you a final. I have to give you some kind of final.
Do you know?
I do because I at least have to give you the post test. So think about what you think a reasonable time frame would be for the lab report. That was one of the things I was going to talk about at the beginning or at the end of class, but I'll talk about it now. No, that's fine. We
No, you continue.
we normally think of ourselves as having a balanced sex ratio, 50% male, 50% female. And for a long time, and your book talks about this, for a long time, we just kind of thought that was the norm and that all organisms were this way until, of course, like everything else in biology, when you look at it a little more closely, you realize that the thing that you thought was true is actually not true. Something else is actually true. So when we think about sex ratios, oftentimes in your background, you've probably dealt primarily with organisms that have what we call chromosomal sex determination. The sex that you are is determined by the chromosomes that you inherited from your parents. In humans, if you have two X chromosomes, you are a female, and if you have two Y chromosomes, you are a male. For the moment, I'm going to set aside all of the exceptions to that, and there are numerous exceptions to that, even in humans. And I'm also going to avoid all of the social and political implications of that. But let's just assume simply for now that in humans, two X chromosomes make you a female, and an X and a Y chromosome for that last sex chromosome pair makes you a male. And the assumption has been that in those organisms, the sex ratio is simply determined by random chance, and random chance will result in a 50-50 sex ratio, assuming that your population is big enough. But then we have environmental sex determination, which is different. This is a situation where aspects of the environment influence the sex ratio. We see this most commonly in reptiles. It's really well known in reptiles, where temperature will oftentimes influence the pathway to determining sex. And then we have some organisms that go through sex changes during their lifespan. And so they'll behave and act and be physiologically one sex at one stage of their life and then change to the other sex at another stage of their life. And so sex determination is much more complicated, and so sex allocation has become more complicated as we've once again learned more and more about the organisms around us. So these are just some examples of chromosomal sex determination. I've already talked about mammals. We have the XY chromosome. In birds, they have a different lettering system, but it's just the opposite. Birds, the ZZ, the one with like chromosomes are males, and the ones with different chromosomes are females. And then we've already talked a couple of times now in this class about haplodiploidy. This is what happens in social insects, where you have males that are essentially unfertilized eggs and females that are made up of fertilized eggs. So the males in this case are all diploid. I'm sorry, the males in this case are all haploid rather, and the females are diploid. And it's the queen that controls the sex ratio to a certain degree. So the queen is the one responsible for producing the offspring. If she fertilizes the eggs, it becomes female, and if she just lays an unfertilized egg, that unfertilized egg becomes a male. And so this leads to conflict that we talked about back in the family conflict situation. Males share 100% of their chromosomal makeup with the queen. Everything that they have from the queen, they only got from the queen. Females, though, share half of their chromosomes with the queen and half with whatever drone the female queen mated with. But as a result, they share more in common with their sisters than they do, for example, with their brothers. And so this leads to conflict within social insect communities, in that the daughters want the queen to produce more daughters and fewer sons, whereas the queen, that might not be what is best in terms of her overall fitness. She should be investing in both equally, essentially. In environmental sex determination, we have a variety of different situations. In some cases, this is the ratio of males. So in some cases, cold temperatures produce 0 males and only females. Warm temperatures produce 100% males and no females. And then there's these intermediate temperatures at which the sex ratio is mixed. So all females, all males. In turtles, it's just the opposite. Cooler temperatures tend to produce males and warmer temperatures tend to produce females. And then in the snapping turtle, which is one of the best studied turtles in terms of environmental sex determination, males are produced at intermediate temperatures and females are produced at the two extremes. So environmental sex determination, in this case, it's temperature-dependent sex determination, which is a subset of environmental sex determination. The temperature at which you are incubated determines which sex you ultimately become. Not only that, there's usually a relatively narrow window during which you are exposed to these temperatures that determines your sex determination. So it isn't the entire development in the egg that determines it. It's usually some critical window when those temperatures are experienced. And then the temperature can fluctuate at other times and it won't have any effect in reality. Because inevitably, these animals are laying their eggs in environments with variable temperatures. Now they're digging holes and putting their eggs in these holes for the most part. But imagine that you're a turtle out on a landscape and you crawl out of your pond. Let's say that you're a snapping turtle, which we're starting to see them moving at this time of the year. You come out of your pond, you go up the hill, and there's a tree. And let's say that you happen to come out of your pond on the south side of the pond. And you dig a hole and you lay your eggs down in this hole. Because you're on the south side of the pond and because you laid them downslope from this tree, the sun in the northern hemisphere is usually off to the south, such that as the sun is passing overhead throughout the day, this particular site happens to be shaded by the tree. So this particular site tends to be on the cooler side, and so it will tend to produce mostly males. I'm sorry, not mostly males, mostly females because it's a snapping turtle. But then on the other side of the pond, another turtle comes out. There might be a tree on this side of the pond as well, but because this is on the north slope of the pond, she digs a hole, puts her eggs in there. These eggs are now getting the full force of the sun coming down on them. They are warmer. And if they're warm enough, they actually also produce females as well. And so where you are in the environment ultimately determines your sex ratio of the offspring that you have. And the way this works out in the end generally is that if you have enough turtles laying eggs in enough different kinds of environments, you get some really hot nests, you get some really cool nests, you get some intermediate nests, and you have enough of that going on that you end up with getting a relatively even sex ratio by the time it's all said and done. Because while this is a cool nest and while this is a warm nest, somewhere else somebody's laying eggs in a nest where there's an intermediate temperature. Now there's a lot of theory as to why temperature-dependent sex determination should be favored by evolution, but the literature on that is really equivocal in many ways because testing this is very, very hard. And I'll explain why. The theory of why environmental sex determination, or in this case temperature-dependent sex determination, works was put forth by J.J. Bull, Jim Bull, who co-authored that? Was it Sharnoff? Well, anyway, Jim Bull at the University of Texas at Austin. I should remember this. I wrote a paper about this. Why can I not remember this? Well, anyway, the idea that they have is that under temperature-dependent sex determination, if you are incubated at low temperatures and you are female, you will have higher fitness than if you are incubated at low temperatures and you are male, in which case you will have lower fitness. Similarly, if you are incubated at intermediate temperatures and you are female, you will have low fitness. And if you're at intermediate and you come out male, you have higher fitness. And then for the highest temperatures, once again, this is for the case if you're a snapping turtle. At high temperatures, they tend to produce females, and if you're a female producer at that, you have high fitness, and if you are a male, you have low fitness. And so the way you have to test this is you have to do something experimentally where you can control the sex ratio in such a way that you get mixtures of males and females at particular temperatures. So what you would want to do is you would want to somehow produce males at a temperature that normally produces females and produce females at a temperature that normally produces males and produce males at a temperature that normally produces females. And so that's hard to do in an incubator. And so what did happen is there were some kind of elegant experiments where they actually controlled the sex of offspring turtles by essentially either giving them aromatase inhibitors or an aromatase inhibitor basically changes the pathway by which hormones, the sex-determining hormones, get altered and turned into either estradiol or dihydroxytestosterone. And so they could add hormones to the eggs and control the sex of the turtles regardless of what temperature they were being incubated at. And under those conditions, they actually found that males that were produced at temperatures that normally produced females actually had lower fitness, and females that were produced at temperatures that would normally produce males also had lower fitness. So there's been one good experimental test, but because it's really difficult to control the sex of individuals through temperature, there haven't been very many good experimental tests of this Bull-Sharnov model of how temperature-dependent sex determination actually works. So, Ronald Fisher was a biologist back in the 1930s and 40s, and he did a lot of quantitative genetic work, a lot of theoretical genetic work. We've already talked about Fisher's runaway selection hypothesis, dealing with runaway selection in trait evolution in sexually selected characters like the widow bird's tail and things like this. But Fisher did a lot of other things. Other than that, one of the things that he did was he thought about this idea of equal investment in offspring. This was a topic that vexed Darwin. Darwin could not figure out really why there should be equal sex ratios, even though back then that was viewed as kind of the normal state of things. And so basically what Fisher said is, if one male can fertilize 20 females, why not have a 1:20 sex ratio? This would maximize population growth. If one male can service 20 females, then males have high reproductive success because they're spreading their gametes around a bunch of females. But this implies that high population growth is the thing that you're shooting for. And that's a very group selectionist sort of argument, because if we think about individual selection, if you are a mom and you are going to reproduce, let's think about this. I think I have a slide, the next slide. You're in this population. So you're in a population with a bunch of females and you put one male out there. That one male mates with this one female. This female then has a choice. It can produce either one female and another male, or it can produce two females, or it can produce two males. In this case, what is it better to do if you're this female? From a fitness perspective, in this environment, you started off with one male and 20 females. Now you have two males and 21 females. What's the fitness value of the males and the females in this scenario? Males are more fit. They have 20 times the reproductive capacity of the females. So males mate with 20 females. Let's assume for now that each female only produces two offspring. That gives the female a fitness of 40. What's the fitness of each female in this situation? Hmm? Well, she produces two offspring. Doesn't matter how many males she might mate with in the process of doing that. All she's going to produce is those two offspring. So it's two offspring total, which relative to the male is 1/20th of the situation. So in this case, if you're a parent, is it better for you to produce males or is it better for you to produce females? It's better to produce females because, if it's better to produce males because males have higher value. And they have higher value because there are so few males, they have a lot of females to mate with, they have 20 times more reproductive capacity than any given female does. So under this situation, males are more valuable, and by that I mean they have way higher fitness. So if there's a gene in the population that, or a variant of a gene in the population that forces you to create more males than females as offspring, then that gene will spread through the population faster because it will be propagated, because that will be passed on to males that have tons of females to mate with. If you have a variant of that gene that causes you to make only females, that allele will not propagate through the population because that will only be found in your two daughters and their two daughters and their two daughters, as opposed to the variant that causes you to make only males that will be passed on to your two sons and their 80 offspring that they produce with the 20 females that they reproduce with. And so very quickly, that variant of that gene that controls sex ratio will spread through the population until what happens? You have this gene that produces nothing but males. It spreads through the population. You might get to the point where there's a male bias. Once there's a male bias, what happens to males and females? The other gene becomes higher fitness because to produce extra males in a population that already has more males than females, it already means that some of those males aren't reproducing. So producing more males in that environment is just wasting them. So any gene that encourages the production of females would become more fit. It would spread. And so you will generally see this oscillation of sex ratio flipping around until you finally arrive at an equal ratio of 50-50. If this population is at 50% males and 50% females, if the females have two offspring, and there's the same number of males as there are females, what's the fitness of the males? Male hooks up with one female, has two offspring. The females all have two offspring. The fitness consequences of being male and female in an environment where the sex ratio is even is the same. So there's no selection pushing for more males. There's no selection pushing for more females. So this is why we tend to hone in on on a 50-50 sex ratio. So some people thought that they would test this. This is the work of Alexandra Basolo, who works on fish genetics. What she did basically is she manipulated the sex ratio in lab populations. So she keeps around large populations of fish in tanks that she can experiment on. And so she just took some tanks and removed a bunch of males from the tank so that it was a female bias sex ratio. And in other tanks, she removed a bunch of females so that it was a male bias sex ratio. This is the sex ratio where it's the proportion males from all males to 0 females. And when you reduce the number of males, the response in the next generation was those females produced a bunch of, proportion male. Remove all the males, so you have very few males and a lot of females. The response was they produced a bunch of males to compensate for that, which drove the sex ratio way up. And then in order to compensate for that, the next generation produced a lot more females. And so it honed in after only 3 generations on this 50-50 sex ratio. In a similar way, when you started out with a lot of males, the fish compensated by producing more females. Once you had a female bias sex ratio, they produced more males. And once again, after only 2 or 3 populations, you kind of honed in on this 50-50 sex ratio. So selection acted in this case with these fishes to push the population towards a balanced sex ratio, at which point males and females have equal value to the parents. So how can all of this play out? And there are a lot of different scenarios. And your book talks about 2 ways of thinking about this in terms of sex ratios. Imagine that you have a population of organisms. Female produces daughters. And sons, daughters, sons, daughters, sons, etc. This is a balance ratio of 50% males and 50% females. In this case, the daughters stick around. And the males, the sons disperse, go out on their own and find other families to breed with. They are not interbreeding with one another. With these daughters sticking around, the more daughters you have, might mean more competition for resources. If resources are in limited supply, what would a female be better off doing under this condition if resources are in scant supply? If daughters stick around, they don't disperse away from the mother. The sons do disperse, and the more daughters you have hanging around, the more competition there is for resources. If you don't have many resources, what should a parent invest in? What should a mother invest in? Should invest in more sons. So under resource limitation, if these daughters interact with one another, and part of this interaction is that they make more resources available, then what should the mother do? So these two ideas are known as local resource competition and local resource enhancement. And so the level of resources can influence the sex allocation pattern depending upon how strong this competition for resources is and the degree to which having those daughters around helping actually improves the situation for resource availability. So under local resource competition, this is a graphic from your book. What you have is an equal sex ratio here. You have the sons that are happy because this isn't going to really affect them at all. And the females are unhappy because these females are competing with one another for resources. And so over time, what you should have is a male bias sex ratio, and that male bias sex ratio reduces the competition for resources among the females. Under local resource enhancement, you have a even sex ratio, and in this case, the more females you have, the more resources you have made available because of cooperative behavior among the females. And so if you then have a female bias sex ratio, more resources are available, and then the females are experiencing higher fitness than they would if it was a male biased sex ratio, because there would be fewer females, leading to that resource enhancement. So the cooperative behavior versus competitive behavior of females can influence what the sex ratio response should be in any given situation. So this is a general idea about resources, whether the stress is on competition or whether the stress is on resource enhancement. That then determines the outcome from the perspective of the sex ratio. But we can also think about another form of competition. So we can also think of this in terms of local mate competition. If females are limited in supply, then there are males out there in the environment that aren't able to find a mate. So if any individual produces more males than females, she's just wasting males because those males aren't going to be mated anyway. And so this would tend to push the sex ratio toward a female bias sex ratio because females are more valuable because they are in limiting supply. So one of the general conclusions that you reach after thinking about sex ratios for a little while is the rarer sex is always the more value. If the rarer sex is always more valuable, then selection should push the population to produce more of that sex. Now, if you have a lot of females and you have very few males, a different scenario plays out. So if females are limited, the sex ratio is pushed towards females because they're the rare sex. If males are rare, you might expect males to be more valuable simply because this male can reproduce with these four offspring, or these four females, and this male can reproduce with these three females, and so you have that that value of males and that they have higher fitness, basically 3 or 4 times the fitness of the females. However, if this is a family, you don't really have that situation because if inbreeding is not allowed, either culturally or biologically, um, these males don't have anyone to mate with in this situation. They have to then disperse away from the parental territory in order to find mates. But if inbreeding is allowed, then these two males can mate with any of their sisters, and in that case, you have a situation where males become more valuable, and that pushes us back into this situation where the least abundant sex is the one that is most valuable. So you will have females producing more sons because those sons can fertilize all the eggs of all of their sisters. And so, once again, this led to Fisher, I believe, also did this, figuring out that once again, over time, this scenario will result in an even sex ratio over time. And so what happens is that if you look at a situation where N is the number of females reproducing, as you think about what the sex ratio should be, the sex ratio will be equal to N minus 1 over 2N. And what your book says is what this means is when there are very few is that right? Let me make sure that I've got this correct. Yeah. When there are very few females, the sex ratio will be skewed towards very few males. But over time, as the number of females increases, the sex ratio will converge on a 50-50 mix. So if this is true, we can actually simulate this ourselves. And we don't need a big fancy computer to simulate this. All we really need to do is open up a spreadsheet. So that's not the spreadsheet I wanted to open up. If we have, let's make this whole thing bigger. If we have two females in a population, and this is the numerator, so 2 minus 1 is 1. This is the denominator, 2 times the number of females is 4. Then the ratio of males in the population should be 0.25. As we increase that to 3 females, the numerator becomes 2, the denominator becomes 6. That's 33% females. Bump it up to 4, numerator of 3, denominator of 8, 0.375 to zero point 0.4 for 5 females, 0.416 for 6 females, etc., etc., etc. And as you get higher and higher, as you get more and more females in the population, you converge on 50%. Oops, I did something. Stop it. And it's basically going to asymptote at 50%. And when you look at a graph of these data, what these data look like are somewhere else on the spreadsheet. These data look like this. So as the number of females increases, you go from a female bias sex ratio to a male bias sex ratio, because when there are fewer and fewer females, then when there are fewer and fewer males, the value of males is high, which encourages females to produce more males in response to this. And if you look in your book, you have a figure that is taken from a set of observations on parasitic wasps. So this is the output of that thing that I just showed you. And what you have in this wasp situation is these wasps are parasitic on the pupae of butterflies and moths. And what you will find is that when this moth lays her eggs in this pupal case, those eggs will hatch out. The larvae will feed on the developing pupa, feed on it until it kills it actually, and then these wasps will pupate inside of the pupal case, and they will mate with one another before they emerge from here. And so in this case, you have a bunch of brothers and sisters who are all mating with one another. And when you look at the number of different females that are laying their eggs in a given pupal case, one of the things that you find is that as that number goes up, the ratio of males to females that you observe in those situations increases, just as would be predicted by theory. And so these ideas that sex ratio is somewhat fluid in response to the prevailing situation where resources might or might not be limited, and where males either can or can't mate with their siblings, will determine once again what the outcome is. And in this case, the outcome is convergence on an even sex ratio. So there's another figure. Figure 10.5 in your book shows this when they gave females either parasitized pupal cases, unparasitized pupal cases, and looked at how that affected sex ratio, and you see that it's going in the same direction that you would expect it to. Birds, this is the Seychelles warbler. This is another one of those situations where resource availability is super important. So we have different years here. 1995 is split into two different figures. In this case, it's very similar to the scenario that I laid out for you earlier. You have females that produce offspring. The females, the daughters, usually hang out. They don't disperse. They will actually help the mother raise the offspring, and the sons tend to disperse. Once again, the y-axis here is the proportion of males. In situations where resources are low, poor quality habitat, poor quality territories, you tend to see sons being produced more. Let's just do. When resources are high, you tend to have more daughters. Why would these two things be true? So this is what they observed. My question is, why do you tend to produce more males when resources are low and more females when resources are high? Okay, so if having more females competes for resources, then when there are very few resources, you want to produce more males because that reduces local resource competition. And when resources are high, then local resource competition isn't as strong. The 1995 data here are split out into nests as a whole versus nests with fewer than one helper or more than two helpers. In this case, both the very few helpers and lots of helpers are virtually the same in low quality environments, meaning that when resources are low, regardless of how many helpers you have hanging around, it's better off to produce more males than females. But as habitat quality goes up and you have more resources, in the situation where you have the most resources, if you only have one helper, what does that do to your availability of that resource if those females are working cooperatively to enhance resources? If these daughters are helping, they're basically enhancing resources. If you only have one female helper hanging around and resources are good, or if you don't have, I guess that's less than one, isn't it? Or oh, it's one or equal to. I guess it's a less than or equal to. So mom with multiple helpers versus mom with a single helper. So that's what this line is versus this is the mom on the right, this is the mom on the left. And why would that be the case? Okay. So in this case, with fewer helpers around, there's less resource competition. Even if resources are high, fewer helpers means less resource competition. If you have more helpers sticking around, those more helpers may actually enhance resources, but it all depends on how much the resource availability is enhanced versus how much is degraded by competition. In this case, all you really need is one helper in this case. One helper enhances resource availability without involving a lot of competition for resources. But as soon as you get above one helper, you start to have some resource enhancement, but the cost of having those extra helpers around increases the chance of local resource competition, which then pushes it back to a male-dominated sex ratio. So this is where the balance between resource competition and resource enhancement comes into play. You can't just think of one of these or the other of them. You have to think about both of them in concert. So we've talked a number of times in here about cost-benefit ratios. You might think that the cost to benefit, helper number one, the cost may increase 1 unit, but if that one individual makes twice as many resources available, that's still a good deal for the parent. But if the second helper increases the cost by 1, but only increases the benefit by one additional unit, you now have a cost to benefit ratio that is 2 to 3 rather than 1 to 2. Raise that to 3. If that thing really increases the cost once again, but once again only provides half the benefit, you now have a cost of 3 to 3.5. Add a fourth, adding a single cost, but now this is down to 0.25. This is now 4 to 3.75. And these are just made up numbers, but you can see why in an environment where you're harvesting resources, one individual can do pretty well. A second individual isn't going to add necessarily the same thing that the first individual added. The third individual isn't going to necessarily add to that. So the benefit per individual goes down over time, but the cost per individual remains the same and just adds up. And so you finally get to a point where the costs outweigh the benefits, and at that point, it doesn't do you any good to have any more helpers. And in the case of this particular example with Seychelles warbler, it happens to be a situation like this. So perhaps it's something more like this. The cost to benefit is more like 1.1 to 1.125, and then as the benefit falls, it falls to 1 to 1, and then anything beyond that is just not worth having helpers around anymore, in which case at that point you should start shifting to producing more males, because the benefits of having more female helpers doesn't really gain you anything. And this is where Trivers and Willard's model comes into play. So if you look on page 297 in your book, there is this figure that we'll get to here in just a minute, where resources available to organisms depends on their condition. So females in better condition have more resources. As a result of that, they can produce better quality offspring, and higher quality offspring become higher quality adults. But sons gain a greater fitness benefit from being of high quality than females do. Under what conditions would this third assumption be true? When do better quality males do better than better quality females? Hmm? Now I'm thinking of a mating system. What's a mating system where male quality is important?
When they do like.
Hmm? So if females are mating with multiple males, that basically means that males don't have a lot of control over who they can mate with, which is why they're teaming up with other males. So probably females are in short supply to the point that you get polyandry. So we have monogamy, polygyny, polyandry, promiscuity. Those are your choices. Under what conditions is a male going to need high quality in order to defend a territory or defend a resource, et cetera, et cetera? Polygyny. So this would be true in polygynous situations where the male is competing with other males for access to either resources that females need or access to the females directly themselves. So this would be a situation where male-male competition is a thing. What happens under this situation is that the quality of the mother accrues benefits to both female offspring and male offspring. The higher quality you are as a mother, the higher quality your offspring will be, but the benefits that accrue to males and females are different. For daughters, it's a linear gain in fitness, whereas for males it is an exponential gain. And the whole reason that it's an exponential gain for males is because in these polygynous situations, the most dominant males have access to the most females. And so as you increase the quality of sons, better and better quality sons gain more and more matings because they're in a polygynous sort of situation. So where these two lines cross is this boundary line between, based on the mother's quality, her body condition, when she should be producing sons versus when she should be producing daughters. When the mother's condition is low, she should produce more daughters than sons. And when the mother's condition is higher, she should produce more sons than daughters, not because of her fitness consequences, but because of the way condition affects the fitness consequences of her offspring. And this is something that was developed in the context of thinking about red deer. This is a deer that occurs in Europe, and it is well known for having males maintaining large harems. They engage in aggressive behavior where they're locking horns with one another. Red deer are well known for having very large and elaborate antlers. And as it turns out, when you look at the dominant structure of a herd, you have kind of alpha females and subordinate females, and you can actually measure what the position in a herd is. And when you look at the dominance position of the mom and the fitness consequences of the offspring, the open circles are females and the closed circles are males. And what you see is that when you look at the effect of the female, the mother's dominance on the offspring lifetime reproductive success, the plot for females is essentially flat. These are all females, all these open dots. If you're a high quality female and you're producing daughters, you don't have any better success, reproductive success in those daughters as if you were a low quality female producing daughters. But if you're a high quality female and you're producing males, high quality females tended to have a lot of males with really high lifetime reproductive success, whereas low quality males produced from low quality females, lower dominant females, tended to have low lifetime reproductive success. So this is the gain curve for female offspring. This is the gain curve for male offspring. And so the sex ratio that you produce should be cued to what your dominance position is in this dominance hierarchy of deer. If you're high quality, skew more towards males because those males are going to have higher lifetime reproductive success. Because the environment varies a lot, body condition may change from year to year. And so one year, it may be more valuable to produce female offspring because food resources are low, and as a result, your body condition is low. The next year, maybe you got a lot of rain, you have good forage, your body condition is good. During that year, you should then put your energy into creating males because males are going to have higher reproductive success. So variable environments can lead to variation from year to year, depending upon kind of what your condition is. Questions? We will reconvene on Thursday. Thursday, meet at the regular time at the beginning of lab, up in the lab room. We will talk about data. We will talk about what it means. We will talk about kind of the structure of your paper. And then we will decide, hopefully, when you want to make that due. And then we will meet again on Friday. Are you guys doing anything for Billy J Day or whatever they're calling it?
I want to come look at the exotic pets.
You're going to come and look at the exotic pets.
I really want to see it.
Where are the exotic pets coming from?
I don't know. We also had exotic pets the other day, so I assume there's like.
Yeah.
I was also wondering, how do you transport like a large alligator?
Some exotic pets for pathetic college students company?